Aarti Bagal, and I'll be your host for the main stage, which is where you're at, as well as for the data track today. So after this session, we'll be splitting up into 3 tracks, the data track, the techniques, and the application track, and you can check out what sessions are coming up in each of the tracks in the agenda tab at the top of your screen. And as you're listening to this next talk, again, we encourage you to put your questions in the Q&A tab. We will be taking those at the end of this talk. So up next, here to talk about programmatically creating training data for machine learning, please welcome to the stage Principal Data Scientist at Memorial Sloan Cancer Research Center, Subratha Chatterjee, and Bioinformatics Engineer at Memorial Sloan Cancer Research Center as well, John Cadley. Hi, John and Subratha. Really excited to have you.
Thanks, Aarti.
Of course. Over to you, and I'll be back for Q&A at the end.
Okay. Let me go to media. Share. Okay, great. So can you guys see my slides? Aarti, can you see it?
I can see them.
We can see it.
Okay.
We can
Okay. Okay. So we are a small team. So let me give a quick intro who we are, and then I will jump right into the slides. We are a small team at Memorial Sloan Cancer Center. We deal with cancer patients. All our patients have some form of cancer, whether they're starting with cancer regimen or they're metastasized into some kind of other organs. We are applying AI ML to different use cases in this project. And John and I are working with, with basically one of the biggest challenges we have is how do we label data. Label means attaching labels to our text data. For example, does the person from a radiology report, does the person have a fracture? Looking at a smoking clinical report, does the person have a history of smoking into different categories, never smoked, ever smoked, and so on and so forth. Then we are going to show you 2 use cases which are different in their applications. One is looking at HER2, and the other one is actually looking at derm reports, skin, where to look at different level of malignancy in the tumor in the skin. So the reason we are here is because we want to show you guys how we took this approach of taking data that is mostly unlabeled with a few labeled cases, and how we applied Snorkel or weak supervision for that matter to get to where we wanted to get to, right? So next slide. Okay. So like I said, the biggest challenge here is that we have in any AI ML project, right? The biggest challenge, especially in clinical area, is that we have a lot of data, but if we want to do some amount of supervised modeling, like, where we need the label of the data, we really don't have it, right? And we can go on this is from one of the people at Snorkel itself, Alex Ratner, who was very, it was very nice to meet him at MSK. He came over to MSK and gave us a talk also. So, if you do it in if you just use human labelers, especially because our labelers are going to be physicians, most of the case, and researchers, the time is very expensive. We are basically doing in a linear fashion, right? So, it takes time and a lot of time to do labeling. And another problem that we found that a lot of the labels that we have in our data are what you call static, right? If you do the human labeler. So they'll label into 2 or 3 classes, and then suddenly we say, no, we want the disease to be classified into 3 more, 5 classes. Then what happens, right? So we were looking around, and we came across this approach, which is called, labeling programmatically. So, and where it is fast, easy, and, we can change the dynamic means that we can change the labels very quickly, the number of labels, the number of classes that we have in the data very, very quickly. Next slide. Yeah. So the reason for this particular slide is I wanted to show you that we did not just jump into this. We saw, oh, great, there's a company called Snorkel, or there's a whole bunch of weak supervision out there. We just take it and try it as an experiment for us. We looked at, we studied the area very carefully, and any clinical project we do, we actually look at the literature to see, has this been applied in the area of clinical sciences, right? And when we looked at it, we found a lot of reasons as to why this approach or this kind of technique may be useful. And I gave you a few examples, right? So like we are, looking at gene expression, which is something that John is going to talk about. Then one of the other things which is very interesting for us, which is the upper right hand corner, is we are looking at something, where we take a report, which is a text report, and then we want to label the corresponding image to it. For example, a cat image, a computed tomographic image, or a MRI image based on the text data. Can we get labels from the text which we can attach to the images? Because labeling images is very intensive. These are three-dimensional images, and they could be thousands of slides just for one patient for one visit, right? So and then what we found is that this particular approach allows us to take a small label data set. So our physicians and all that, they have manually went in and curated a small set, and then they're saying, okay, we can work with you to give you some general rules of how we curated this data, but we cannot just curate the rest, 10,000 patients. So that's why we found that you have a small label data, but we have a large volume of unlabeled data. How can we do this, right? And another interesting part, the last point I want to touch on, is that because we are using this concept of rules or regexes really to start with, to label our data, it is much more transparent, like rather than using a very powerful deep learning method, which is a black box model, right? So what we are thinking that we can use this working of the model, and it will show to us why did it label a certain thing in a certain way, which is very, very, very important for us to remove what we call medical bias and model governance in the future, which is something that we are looking at very, very closely in clinical space. Let me go to the next slide. So this I think people have already seen this, so I'll not spend time. So I use this slide to show how we did it. Basically, we have humans who create some sort of a labeling functions, basically regexes, right? If you cannot see this a little bit, but it's in the paper that I cited below, just rules, right? And the rules could be conflicting with each other. So that's the idea, right? So what happens is a labeler can write simple rules that have what we call wide coverage, and in our statistical literature we call this recall, right? So they have very high recall but very low precision, right? So they say, okay, if a vein is showing up in the leg and it has this measurement and is showing up this, then the person probably has what is called venous thrombosis, right? But that's a catch-all kind of phrase, and it's going to have very low precision in it. And what this model does with the approach that we are talking, and this is nothing new to Snorkel. There's a whole bunch of papers out there that talk about weak supervision, but the Snorkel power comes in later on. Actually, I'll show you why. And so in this case, what it does, it takes these different labels and they look at agreements and disagreements, almost like a mixture of experts model, or if you think of a jury in a courtroom kind of thing, and they create what is called probabilistic labels, right? So for each patient, we have a probability of what this patient is falling into each of those classes, and it assigns those labels, right? And then what this model does is you can put a classifier on top of it, which it could be anything. It could be a deep learning model, it could be a BERT-based classifier, it could be XGBoost, whatever you work, and then you get the results out. Now, what the power of Snorkel is actually the last part, is where it actually comes back and tells you, hey, John Subrata, you wrote these labels are contradictory. These labels, if you change it, if you go here, if you change these are the cases where it is showing mislabeled, is going to tell you, right, what is happening. And for comparing, you need the ground truth. So you need a very little ground truth really to look at it. But in the ground truth is not used anywhere in the model. It is basically used to assess your model performance in the end, to see and to figure out where the labels that you have attached or the labeling functions or the rules that you have written are actually not right. So I want to jump in the use case. I know we can have time. So like I said, there were two use cases. The first use case was about identifying, what we call the HER2 strain, and John can talk about this. I just want to give a quick preview on this. So basically this, as you guys can see, what in machine learning, this is a multi-class problem, right? And it's a very unbalanced problem that you can see. And we have all these labels. So the thing about this particular use case, is that we have these labels already done. These are not really a way to test Snorkel performance in that sense, whether it can label a new set of data. We did not have any unlabeled data in this case. The reason we chose this particular use case is because we want to see, does it really do good? because we were suspicious of this thing, right? We are not reading the technology, going deep into the equations and all that. We want to take the snorkel, the weak supervision from it, and test it on this particular use case to see if it really does what it's supposed to do. And that's why we chose this. And John will take you through next. John?
Okay. HER2 is a protein that shows up in a lot of cancers. It's human epidermal growth factor receptor number 2. And from the sound of the title, you can probably tell that it's one of the things that makes cancer cells multiply a lot. So we have some drugs that if you have a cancer that's HER2 positive, that means this is one of the mutations that's wrong with you. We can deal with you with the drugs, and if you don't have this, then we have to use something else. So it's important for us to be able to know whether you have this, both for clinical studies and for doing retrospective studies. That's kind of the point of focusing on this protein. And the way you interpret the labels in this left-hand column here is if you do the test that tries to figure out whether you're HER2 positive or not, if you get a 0 or a 1, that's considered negative. That means you're not overexpressing this protein and something else is wrong. If you're a 3, you're definitely positive, and there's something we can do for you, we think. And if you're a 2, that means the test is unable to figure it out. It's equivocal, and there's another more detailed test that we can do to actually distinguish between whether you're negative or positive. The reason this more detailed test isn't used all the time is that it's quite a bit more expensive and time consuming, so we'd rather not use it if we don't have to. So the reports that we get from patients, the pathology reports, usually have one of these 4 categories in them, but sometimes there's no reference to HER2 at all. Just no test was done and we have no idea. So that happens about half the time. So this is what we're dealing with. We have a database of over 3,000 pathology reports, and we want to see if Snorkel can extract these labels out of the reports. This is an example of what the interior of the reports look like, just small parts of them. So for example, in this first patient, here's how HER2 shows up. It's buried with NEU. The immunostain is negative. Negative is a synonym for 0 plus. Here in this particular report, they've also tried to show us that 0 is what they intend, except they typed in the capital letter O rather than 0. So we would like Snorkel to be able to figure out that this sentence here means 0 plus. Here you can see 3 plus is 3 plus. That's pretty simple. This one here is 2 plus, but also the word equivocal sometimes just shows up all by itself without a number. And we'd like Snorkel to be able to figure out that, oh, those cases are 2 plus cases. Here's how we distributed our reports for purposes of the study. We had 3,000 reports. We threw 500 of them into a validation set that I cycled on when I was doing my my labeling functions. We had 300 reports that we used for our final testing, and the training reports we used some of our ground truth labels to help do the label function development. And the other 1,800 which had no ground truth associated with them, or for our purposes, we used as a training set. After running Snorkel a couple times and only really having at this point 8 labeling functions, this is an example output of Snorkel, and I put this up because it wasn't our final version of it. This is an intermediate version. I wanted to show how this was used. So, for example, if you look at this 3 here, you can see for these 3 reports, the ground truth is 2 plus, yet Snorkel said it was not present. Like, why was that? So I was able to look into this very easily because it identified the 3 reports for you right away. And the problem here was that in these reports, rather than 2 plus, plus 2 was what was in the report. Snorkel in this version didn't recognize the plus 2, so it said there's no HER2 information present here. So by just adding some labeling functions, I was able to make these go away. Here, this 17 and 18, which are plus 2 pluses and plus 3s, you'd think Snorkel could find those, except in addition to having those 3 pluses and 2 pluses, there were also many negatives in the word negative in these reports. So many, in fact, that Snorkel was kind of fooled into thinking that these are actually 0 plus categories. The negatives kind of swamped the quantity of 3 pluses and 2 pluses. And the reason there were so many negatives is there are many other gene expression levels for other genes, non-HER2 genes, that were negative in this report. So I was able to fix this by just saying, oh, just used the negatives that are near HER2, and then these all went away. And I was eventually able to get my F1 statistics all to be in the 90% plus area when I did a few more iterations on this. So we ended up pretty happy with this first cut at using Snorkel to identify HER2. And HER2, this screening system is actually in place now, screening new patients for clinical trials. This is the second use we had for it. This was trying to figure out, or trying to categorize what kind of skin cancer you had from pathology reports. And this is not as simple as the previous HER2 example. These were the 5 categories of skin cancer that we started with. Later, we combined this into just 4 categories because these 2 here were so small. We had 5,000 reports. Only 1,300 of them were actually labeled, so there were well over 4,000 that were unlabeled. And what the reports looked like, or extracts from them, were like this. So the labels aren't buried in these reports. Rather, we had, as you can see, like complicated diagnoses, like squamous cell carcinoma in situ. Which of those 4 categories did that belong into? In this particular case, it was this one. But you can see the labels themselves aren't buried in the text. Rather, diagnoses are buried in the text, and we needed Snorkel to try to categorize them, classify them into eventually 4 categories. As before, we split them up into validation, test, and training groups. And eventually, I cycled through and made 32 labeling functions. And you can see the F1s are all in the 90% plus area. So this did a pretty good job eventually. And there are just a handful of ones that didn't catch. Like if I was going to do more, I'd focus in on this 14, for example, but I stopped here because it was already pretty good. All right, that's the end of our example. So, Brada,
Yeah,
you want to add
yeah,
anything?
I just want to add one more thing. So what we did, when we are showing this, one of the questions that comes up often is that why are you just showing the validation set for people who are in machine learning, right? So we have this separation of train, validation, and test, and the lingo goes different depending on how people think about it. But the test is actually the holdout, right? The actual holdout that the model was never exposed to. So, and the validation really is used in tuning the model, as you can see in the slides that I presented before, in some sort of tuning. We show the validation set just to show, like John said, this is part of it. But then we actually put the performance of the test in each of these 2 slides. In the use cases, you'll see that we have put the performance measure on the test, which is very close to the validation set, just as a way to show you that we are not, showing something that is not realistic. So the performance on the test was slightly lower than the performance on the val, which is expected, and it is good because shows that you are not doing something weird, and that's why we show. So that's one point I wanted to add on this thing in case people have questions. So I think so the next step, what we are doing right now, I didn't put the slides here, but partly because a lot of the work we do is very much tied to research and to people who are writing grants and all that. So it's kind of proprietary at this point. So there are many things we are trying to do. One of the things we are trying to do is look at, like I mentioned about this, and there's a paper on it too, look at smoking status identification. And John is working with me on that. It's a very, very tough, much tougher problem. I think a layer of difference there is there we actually have to do something which is called the temporal nature of the data. We have to figure out whether the person has smoked how many cigarettes over time to get something called pack years. That is very important to researchers in this field. And John is working extensively in this area, and a lot of it is based on regexes and all that. So I will engage with Snorkel research in the very near future to talk about how we can do sort of temporal record work with these kind of platforms. Another place that I haven't highlighted that we are working on is the thing about again the same thing about temporal, but looking at multiple reports over time to find what is called time to event model. In medical work, in the clinical work, our researchers are not much interested in whether the event happened or not. Event being whether you had like in this case, particular protein manifestation or not. but the time to the infestation, to the infection, right? So time to event models, which are called survival models in the literature, we are looking at that to see, because that gives the doctor, the physician, some time to what we call cohort selection, like who are the patients who are more likely to catch a disease. They haven't caught it yet, but we need to know the time. So we are looking at Cox pH models in that area, but we want to see if Snorkel can help in tagging data which have time to event, which doesn't seem to be quite as straightforward as a classification event. So I will just stop there and take more questions. I see a whole bunch of questions on the channel.
Yeah, thank you so much, Subrata and John. Lots of questions popping up. So the audience is definitely very excited and more popping up. Just to quickly touch on the last use case you mentioned, we are actually working with another medical pharma company to figure out this sort of like time to event type of analysis. And that could show up in other ways as well. Like you were talking about cohort selection, but it could always also be, is somebody going to get an adverse event from a drug and then you want to maybe pull them off of it, things like that. So lots of exciting use cases in the domain that we're excited to continue partnering with you on. So just to start with the questions, one that I think was answered briefly, but just to have it as part of the recording as well. Somebody asks, like, do you think you can use human in the loop, semi-supervised techniques as well, like active learning, instead of like a weak supervision programmatic approach? I will add my 2 cents at the end, but would love to hear from you.
Yeah, so I answered that part. So we are using, it's kind of a mixture. So we are using the human. The human is in the loop anyway in this whole process, right? So John, as a human, writes the rules, but then the snorkel comes back, the weak supervision comes back and tells John that, hey, what are the things that are wrong, or these are likely contradictory. We found some very interesting examples in the DERM project, right, John, where we saw that the human actually, you give the same. Well, there could be two issues, right? One is that you give the same text to the human at different points in time and they label it differently. Another is you give the same text to two humans and they label it differently. And if you look at the text, it could fall into either one of the categories. So we have the human in the loop. Well, this concept is already there. So we are doing that for this particular kind of work. I'll leave it short there. The paper actually has a much more details in how this is, it carves out its own space of techniques.
Makes sense. And to quickly touch on the active learning part, and would love to hear, how much speed up you got. But generally we see, again, like as you were mentioning, it is human in the loop. But if you just do active learning, like just having the model prioritize and then manually label, we find that you might get maybe 10% improvement top. Okay. But when you're doing weak supervision programmatic labeling, it's a 10 times or 100 times improvement. So the magnitude of speed up that you get from weak supervision or programmatic labeling is so much more than active learning. And as part of the platform, as John was mentioning, going through the error analysis tools and then figuring out which examples to label. In Snorkel, actually, we combine weak supervision with active learning. So then you get even faster, more of the speed up. That you were talking about.
I can comment on that. It took me a long time to build that regex model. And I read hundreds, thousands of pathology reports to make that work. That's what took such a long time. Whereas it was a few hours to get to what I showed you for the HER2 study. So it was a pretty dramatic difference.
And doctors really like it, right? When they see that, okay, here is a rule, right? If you do these kind of things, it's contradictory. I think that part, the feedback loop, is really useful for our work, so that people can start believing in it and saying that, okay, it's not a black box and it's something that is, we're not trying to explain this statistically using all kinds of heat maps and all those Shapley and all that. We're actually showing them where they are contradicting, and if they did it, how much improvement can they expect? That I think is a great thing.
I could also add something on the ground truth thing. The ground truth gold standard isn't so gold, is what I've noticed. That a lot of times, after you've gone through a couple of these iterations and you've got one of those boxes with what looks like errors, and you look into them, you discover that you think the gold standard is wrong, or or reasonable people can disagree, and I found that to be happening more often than I would have guessed before I started getting into this area.
Makes sense. No, really excellent points around, speed up as well as interpretability, and then ground truth, being able to even discover ground truth being wrong. So exciting to see this out in the wild, things that we're excited about in practice. Great. Moving on to a couple other questions. So for cancer diagnosis, how good is good enough? Like, do you need recall to be 100%? Or, so what do the metrics look like, and when do you decide a model is then ready for operationalization?
I think that's a matter of judgment. I mean, because there's a couple of things you're looking for. Just for example, in the HER2 study, one thing is doing retrospective studies where you're doing statistics. There's a certain percentage that of error that you're expecting to get anyway, and it's kind of your judgment as the researcher to figure out, is the standard of error too wide or is it too little? I mean, it's a judgment call. It doesn't have to be zero because you're not doing it to treat someone. The other use we use it for is for screening for clinical studies. We get many pathology reports every day. No one is reading every one of those to worry about HER2 or any of the other things they could possibly be doing. I mean, there's so many clinical studies. So it's not as if what we're doing now is perfect. We're trying to make it better. In fact, we're trying just to do it at all, just to do a study that screens for HER2 and gets people into a study for gastrointestinal cancers. That's something like we're not doing now, right? Or we do it, maybe somebody looks at a few reports and they go on to their rounds, but they're not doing it perfectly as things are today.
So,
now, of course, for actually treating people, that would be an entirely different standard. I mean, you couldn't
yeah.
have something that's wrong.
Yeah. So on this point, I'll also add some of the statistical. So, in machine, this is one of the challenges of having people in machine learning showing, work to clinicians and researchers in this field. We have this tendency of trying to say, oh, here's a rock curve, here's PR statistics, here is a, contingency table. Doesn't work. So what we are doing in clinical, and that's one of the reasons why AI ML is having a hard time getting into clinical work, is you have to believe in this, that do no harm. It's because a lot of the treatments that we do has a lot of side effects. So treating, and depends on which cancer type, like John was talking about. So I think you have to be careful that you don't give, what we call microwave the patient. Treat the whole patient holistically and say that, okay, we're going to apply this treatment. So we use a host of things. I've not shared everything, but we use not only the rock curves and PR and those tables. They don't fly. So we use something called, and it has been developed in-house in MSK. Dr. Vickers, who's a big person in this area, is called decision curve analysis, where we look at what the trade-offs of doing treatment versus no treatment, things like that. And then we do calibration. Model calibration is very, very important, because like John said, if you want to select a cohort, you want to see if the model predictions for the highest, most risky population is lining up with the actual predictions. So people who are in this area with some, familiar with something called Hausman-Lemon-Schwartz statistic. So we use something like a calibration curve, and we use a checklist. There's actually a huge checklist which has been published by somebody from, I think, Netherlands. So it's called the tripod checklist. We go through the checklist for each of these things to make sure the model satisfies all of them. Otherwise, it's not going to get adopted clinically. Anyway, I stopped there. Sorry to take time.
This is an amazing discussion. I feel like I would love to continue it. I mean, excellent points around like model calibration also, and just a counterfactual analysis of like, if they would have done this, what would have happened versus not.
Yeah.
And even using, as John was earlier saying, like using maybe machine learning models to prioritize what people look at, maybe not just automate. We have unfortunately less time than we would like here. And so maybe what I could end with is what will be the best way to contact you? I know there's a lot of questions in the chat as well. So if people have more questions, what will be the best way?
You send an email, I guess. You have John and our email address. So we'll take all the questions. All questions good. We'll answer each one of them.
Perfect. And then if you are in the chat, please feel free to add your emails as well if you're open to other people reaching out.
Okay, we'll do that. Awesome. Okay.
All right. Well, thank you so much for your time and for sharing all of this with us. Very exciting session. For our audience members, if you would just like to take a quick second to take the poll, tell us what you thought of that session, we'd really appreciate that. And with that, up next, we are breaking up into 3 tracks, as I mentioned. By default, you will now be pushed in about 20 seconds into the data track. But you can go to the agenda tab to also pick the session that you would like to join. So see you there shortly.